want to cover all the aspects one needs to know for the Poisson distribution. This is really just on the fly. Let's see what we can do. Thank you for subscribing to my channel and liking the video. You can always request a topic that you want me to cover, and I will do so. Hope you had a good Christmas. Alright, here I have defined n. N is, what the heck, I put equals, but I meant distributed. We use this little tilde sign. Is distributed Poisson with a mean lambda. And as far as exam P goes, I can't think of an example where they don't tell you something is distributed with the Poisson distribution. There have been times where it may be convenient to realize that it is, actually. Maybe only like one question. Usually, if something is distributed with the Poisson distribution, and as far as insurance is involved, or involved in exam P, usually like the number of claims like per year, or the number of accidents per week, right? So it's a discrete distribution. And again, let's just go over the various things you need to know. Okay. The first one is the expected value. The expected value of the Poisson distribution. Okay, the mean. So what is E of n? Well, first of all, I guess I should write down the PDF. The probability density function, right? Pn of n is equal to e to the negative lambda, lambda to the n, divided by n factorial. All right? We should get here that the expectation is lambda. So, by definition, the expected value is equal to the sum from n equals 0 to infinity of n times the PDF, e to the negative lambda, I did it again, lambda to the n over n factorial. Okay, this is sort of a common trick involving series. It's not really a trick, it's just an observation. First of all, might as well start at n equals 1 because the first term is 0. Okay, so this is equal to the sum from n equals 1. The dogs love barking right when I make a video. It's their favorite. So, the n cancels the n factorial, right? So this is e to the negative lambda, lambda to the n, over n minus 1 factorial. Nothing fancy going on whatsoever. I changed the lower index to 1 because the first term is 0, as well as did a cancellation here. Remember, n factorial is n times n minus 1, etc., right? So that's cancel. What can I do now? Well, we're almost there, really. You can always factor things out that don't depend on the sum, namely e to the negative lambda. So I'm going to take out lambda, e to the negative lambda. Okay, what's left over? I have n equals 1 to infinity of lambda to the n minus 1 over n minus 1 factorial. So hopefully you can see what I did there. I took out a lambda, I took out e to the negative lambda. Why would I do this? Look at what's left over. You can't do this trick if it's a finite series, but if it's infinite, you can absolutely do this. If you want, change the indices, right? Change these n. You could want, if you want, make the substitution n minus 1 equals k. This is exactly right here. I mean, if you're watching this video, you have some experience with this, so you know that this is e to the lambda. This is just the power series representation or Taylor series for e to the lambda. So what do I get here? This is lambda e to the negative lambda times e to the lambda. All right, well, these are the same base. Multiply things to the same base, you add the exponents, this is lambda. All right, what did we just show? Well, we showed that the expected value of a Poisson random variable is equal to lambda, so I'll record this information over here. The expected value is equal to lambda. Pretty straightforward, if you ask me. So the first moment is lambda. Now, what is the second moment? What is the second moment? Because ultimately I want to find the variance. I want to find the variance of the Poisson distribution. You can of course just write down the moment generating function and find the variance that way, but it's not as cool. When I say cool, I mean it's not as interesting, I guess. Maybe you won't think this is interesting either, but I want to do this the direct way. I want to find the variance the direct way. Namely, I have the first moment. Let's find the second moment. Calculate the variance. See what we get. Now this is a trick. A trick. Just like many other things in math, many things involve a trick. So the second moment, right? If I square n, this is equal to the sum. By definition, n equals 0 to infinity of n squared times the PDF, e to the negative lambda, lambda to the n factorial. So same thing as before. I'm going to have to do a little more work though. And here's the trick right off the bat. Because you can't deal with this very well from the get-go, right? I mean, what am I going to do here? You cancel an n, but then I still have another one. So it doesn't really work. I mean, go ahead and try something. It's not going to work. So now what you can do though, however, we can absolutely say, using our algebra skills, and by the way, let's start at 1 again, because the first term is 0. N squared is equal to this quantity here, is equal to n times n minus 1 plus n. Now, looking at this, of course, there's literally, seemingly, no reason why the hell I would do this. Except for that, well, first of all, it's true. This is n squared. If I distribute n squared minus n plus n, it's definitely n squared. Right? This is absolutely true. Why would I do this? Let me show you why I would do this. Because now, this is equal to the sum from n equals 1 to infinity. Distribute this factor, this quantity over here, into here. This is what I arrive at. N times n minus 1, e to the negative lambda, lambda to the n over n factorial, right? Plus, now the sum distributes through a sum, right? Sigma distributes through the sum. Okay, so this is equal to the sum n equals 1 to infinity of n times e to the negative lambda, lambda to the n over n factorial. This is looking good. You should recognize this expression over here because that's the expected value. What about this business? What about this business? So I'm just going to, well, think about it. Okay, you've had time to think. Now, n times n minus 1. And I have n factorial here, but n factorial is n times n minus 1 times n minus 2, all the way down to 2 times 1, not times 0, times 1, right? So, this is equal to the following. This is equal to the sum from n equals 1 to infinity. This cancels here. What am I going to do here? I'm going to take out e to the negative lambda. I'm also going to take out lambda squared. Okay, this is what I get. This is what I get. I get lambda to the n minus 2, but now n times n minus 1 cancels here. This is n minus 2 factorial. Plus, now we recognize this. This is the expected value of n, which of course is lambda. Look at what I have here. Again, and again, well, first of all, this cannot be done unless it's an infinite series, but another observation to make here, if n is 1, this is also 0. This is also 0. So I'm not going to start at n equals 1. I had to pause for a second. This is actually going to start at n equals 2. And thank God for that. Because again, now this is e, this is the power series of e to the lambda again. So this is equal to e to the negative lambda, lambda squared, e to the lambda, plus the expected value of n, which we already know what that is. That's lambda. These, e to the negative lambda times e to the lambda is 1, so this is equal to lambda squared plus lambda. Alright, so there's my second moment. I'll record the information here. The second moment is lambda squared plus lambda. This is not really anything of importance in terms of studying for exam P. It's not something that really comes up that's really useful. But I do want to use it to derive the variance, which is absolutely useful. So this is what we get at for the second moment. Wonderful. Let's calculate the variance. Quite an easy computation at this point. Let's use the definition. So, the variance of a Poisson random variable. I try to act French when I say that, because it is as far as I know, a French mathematician who is no longer with us. Anyways, whatever. The variance of n, we know, you should absolutely know this definition of variance. If you're going to get anywhere in your probability life, you need to know the variance. It's always the second moment minus the first moment squared. We have all the information. This is equal to lambda squared plus lambda minus lambda squared, because I'm squaring the first moment. This is equal to lambda. This, well, let's record it first of all. This is very, I repeat, very important that you realize that the variance is exactly the expectation. You need to know this. Quite important. There are questions that rely on that fact. If you don't know that, I mean, you're just totally screwed. I'm not going to lie. You have to know that. So there we are, the variance. Next thing on the list is the moment generating function. This is absolutely important as well. So let's derive that real quick. The MGF, right? The moment generating function of the Poisson random variable. This is a common notation. M sub n of t. This will be a function of t. We're looking at the sum from n equals 0 to infinity. So let me just write this out. So this is e to the tn times e to the negative lambda, lambda to the n over n factorial. So I kind of skipped an intermediate step, but hopefully you know, right? The definition of the moment generating function is the expectation of e to the t times n, right? It's the expected value of the exponential raised to the t times whatever the random variable is. In this case, it's n. Same trick as before. Actually, I don't even care. Well, actually, the first term is not 0, so I need to leave this. But I mean, there's not too much going on. Just just recognize something here. That we have the following. This is equal to e to the negative lambda times the sum from n equals 0 to infinity. These have the same power, kind of. This is definitely true. E to the t lambda to the n. Is that true? Hell yeah, that's true. I mean, do you even know how to do algebra? Distribute the n in here. Just algebra property, right? Over n factorial. So, why the hell would I do this? Again, recognize, you need to get used to this sort of thing. This is the exponential raised to this power. That's always what it is. I mean, take a trip back to Calc 2, and you should know this. So this is equal to e to the negative lambda times e to the t times lambda. Can we clean it up? Yes, this is not really the way that it typically looks. So this, of course, is now equal to I can factor out a lambda to the lambda times e to the t minus 1. This is the MGF, the moment generating function. We will absolutely record this for information we need to know. So this is equal to e to the lambda, e to the t minus 1. Valuable thing to know. I actually don't see the MGF coming up too frequently, but there is something that I want to use this for, which is extremely important for exam P. Okay, so we've done this computation, we're good to go. Let's get rid of it. A very important theorem, which the last thing I'm going to prove here regarding the Poisson distribution that you need to know, that is definitely on the syllabus for exam P, is that the sum of independent, not necessarily identical, although it would be true for identical as well, is that the sum of independent Poisson random variables with various parameters, various means, is also Poisson. So let me write it down. Write down what I just said. The theorem, which we'll prove using the moment generating function. For these Poisson random variables, say I equals 1 to n, Poisson random variables, okay? Each a Poisson random variable where, let's say this, where, let's say that n I is distributed Poisson with lambda I, right? So the i's correspond, okay? Then, here's the conclusion, then capital N, which is equal to the sum I equals 1 to n of all of these ni's, is Poisson. Is Poisson with mean with equal to sum I equals 1 to n of lambda I. And I left out a crucial piece of information, and that is these ni's must be independent. Okay, independent. Each in the Poisson random variable, we definitely need independent. Independent Poisson random variables, right? We absolutely need that. If we don't, not true. How am I going to prove this? Well, again, I mean, you really just want to know this, but you may be asked something about the moment generating function, which you may need to recognize that this is actually the case. We're going to use the MGF, moment generating function, because it is well known that the moment generating function is unique. Okay, so I watched a video, and I love the way this was referenced. There aren't just moment generating functions masquerading around pretending to be other distributions. In other words, if I have a moment generating function which is of this form, it's automatically Poisson. It's not just some other random variable pretending to be Poisson. So thank God for that. Otherwise, this proof might be quite difficult. So that's true. Let's prove it using the MGF. Okay, so let's do it. I mean, let's just jump right to it. It's not too bad, actually. So what do we have here? So the moment generating function of n, capital N, which is this business, of t, by definition, this is equal to the expected value of e to the t times n1 plus n2 plus plus n, right? Okay, that's what we have. But we know how to deal with exponentials. I mean, we can absolutely say this. This is e, the expected value of e to the t n1 times e, the expectation of e to the t n2, all the way up to the expectation of e to the t n. Those are each moment generating functions right here. I mean, this is the definition of the MGF for n1, MGF n2, etc. So this is equal to this business. This is equal to, now what are our parameters here? This is e to the lambda 1, e to the t minus 1. That's the first one. E to the lambda 2, e to the t minus 1. E to the lambda n, e to the t minus 1. We're pretty much there, right? Because now this is equal to e to the lambda 1 plus lambda n, just using properties of exponents, e to the t minus 1. What did I just say a moment ago? Okay, I didn't prove it. Kind of annoying when this sort of thing is done, but can't prove everything I say. This is the MGF of a Poisson distribution. I mean, here is the mean. Here's the mean. So that does it. I mean, that makes the conclusion true. I mean, this is an MGF. Therefore, so my conclusion, right? N, so hence, n, which is equal to this business, I equals 1 to little n of ni, is Poisson. Poisson with mean I equals 1 to n of lambda I, right? It's exactly what we wanted. It's exactly what we wanted. You absolutely need to know this. This comes up frequently, quite frequently. You need to know this. All right, that takes care of what I wanted to say. That's pretty much everything regarding the Poisson distribution that you need to know. Of course, you need to take, well, you need to practice. You need to do like 1 million examples, because that's how you study for this sort of thing. Please comment below, tell me what you think, and request a video, subscribe, and like. Thank you.